Hello and welcome. Today, we are going to pull back the curtain on a concept that sounds super technical, maybe a little intimidating, Big O. But I promise you, this is not about complicated code. It's actually a really powerful way of thinking, a kind of secret language for understanding how things grow and change all around us. So let's just dive right in with a simple problem you've probably faced 100 times.
Okay, so picture this. You're heading somewhere new, you plug it into your map app, and you get two choices. You can see Route 1 is shorter, distance-wise, but it's full of traffic. Route 2, on the other hand, is more miles, but you can go a lot faster. This brings up a really basic question.
Which route is really the best one? I mean, what does best even mean here? Are you trying to save on gas, or are you trying to save time? To make the right call, we need a way to measure these trade-offs. And you know, this whole idea of measuring what's most efficient, it pops up in some really surprising places.
In fact, that exact same puzzle, finding the most efficient way to do something, is at the very core of computer science. It's never just about getting to the right answer, it's about how you get there.
So check out this real-world example from a Stanford programming class. Students had to write code to find something called perfect numbers. Don't worry about what they are, it's just a type of number. Now, the students came up with 3 totally different ways, or algorithms, to solve the problem. And here's the kicker. All 3 of them worked. They all got the right answer, but the way they got there was worlds apart.
And the results were just wow. Take a look at this. To find the exact same number, the first method, which was basically a brute force search, would take literally weeks, maybe even months. The second, a slightly smarter way, took about half an hour. But the third method, using an ancient trick from Euclid, less than 1 second. This shows you in the most dramatic way possible that your strategy, your approach, matters a lot.
Now, to really get a feel for this, let's forget about computers for a minute. Let's just play a little game to build our intuition about how things scale up in the physical world. You ready? Okay, first up, we've got a square plate. It's 10 meters on a side and it weighs 100 kilograms. Now, if we double the side length to 20 meters, what's your gut feeling on the new weight? You might be tempted to say 200 kilos, right? Double the side, double the weight. Makes sense. Go ahead, lock in your guess. The answer is actually 400 kilograms. So why? Well, when you double the sides of a square, you don't just double its area, you quadruple it. 4 of those original squares fit inside the new one. And since the mass comes from the area, the mass quadruples too.
All right, you ready for level 2? Let's take it up a dimension. Now we have a 10-meter cube, also 100 kilograms. If we double its side length to 20 meters, what do you think happens to the mass this time?
It jumps all the way to 800 kilograms. That's because we're in 3 dimensions now, length, width, and height. So when you double the side, the volume goes up by a factor of 8. 2 times 2 times 2. See the pattern?
Okay, final puzzle, the boss battle. Here's a statue. It's 10 meters tall, weighs 1,000 kilograms. What if we scale it up and make a version that's 3 times taller, keeping all the proportions exactly the same? What's your prediction for its new weight?
An unbelievable 27,000 kilograms. That is massive. Tripling the dimensions doesn't just triple the volume, it increases it by a factor of 27. 3 times 3 times 3. This is what you call cubic scaling, and as you can tell, it gets out of hand really fast.
And here's the really cool part, the key takeaway. Even if we had no idea how to calculate the exact volume of a complicated statue, just by understanding this basic principle of how it scales, we could make a pretty darn good guess. And that idea, that's everything.
And now, finally, we can put a name to this language of scale that we've been exploring. It's called Big O notation. This is just the formal, kind of nerdy way of describing exactly what we just saw with our own eye.
So what is it really? It's simple. Big O is just a way to talk about the growth rate of something. It's not about the exact precise number, it's about the trend. It answers the question, if I change this input, how much does the output change? And that O, it just stands for on the order of. It's basically a shortcut to say, hey, we're not worried about the nitty-gritty details right now, we just care about the big picture, the general shape of the growth. So let's go back to our simple square to see this in action. If we call the side length r, then we know the area grows in proportion to r squared. So in the language of Big O, we'd say the area grows on the order of r squared, or just O of r squared. That's it. That's the secret language.
Okay, now that we kind of get the concept, let's go looking for Big O out in the wild. You'll be amazed at where this secret language starts to show up.
You ever wonder why you can't see a single living cell?
Why they're all microscopic? Well, Big O has the answer. A cell gets its food through its skin, its surface area, right? That grows at a rate of O of R squared. But its needs, its metabolism, that's based on its volume, which grows way faster at O of R cubed. So eventually, if a cell gets too big, its needs literally outgrow its ability to eat. It's a physical speed limit set by two different growth rates.
Or how about this one? Metcalfe's law. It's a fancy way of saying that the value of a network, like a social media platform, grows on the order of the number of users squared, O of n squared. This is why those networks can explode in value. To make your network 100 times more valuable, you don't need 100 times more users. You just need 10 times more, because 10 squared is 100. It's this incredibly powerful nonlinear growth.
So, we've seen Big O in computer code, in physics, in biology, even in business. The last step here is to take this new lens and start looking at your own world through it. Seriously, think about it. Once you start looking for these scaling patterns, you'll see them pop up everywhere. Like, if you double the number of people coming to a party, does it just feel like double the work, or does it feel like it quadruples the chaos? When you add one more person to a work project, how much does the complexity really increase? The language of Big O gives you this whole new toolkit for understanding the world. So what are you going to see with it?